thank you guys for coming out today. And what we'd like to do today is run through some tips and tricks for analyzing large models in SOLIDWORKS. And it's something we're asked about all the time. In fact, it's one of the most popular blog searches on our blog is basically tips or advice on analyzing larger assemblies. So let's see what we're going to cover today. Now, I'd like to go over some overall strategy for larger assemblies. And as long as you keep some things in mind and you go through a certain, I guess, set of steps, large assemblies do not have to be hard to analyze in SOLIDWORKS. They can be a little tedious, but the whole point of today is to show you some things to speed that up. So we're going to talk about element type selections. We're going to talk about symmetry, 2D simplification, automatic contact set definitions, submodeling, and then some solver choices specifically for large assemblies. And hopefully this is going to help take some of the mystery out of what you should be doing with large assemblies and then hopefully point you in the right direction. So what we'll do, guys, we're going to start with some overall strategy on large assembly simulation. Now, as we know, analysis with lots of parts and bodies can be frustrating, and some of the things that are going to make that easier, guys, are starting with simplification. And we'll talk about this as we go, but simplify as much as you can. If you're trying to analyze a 100-part assembly, you probably have some components in there that could be taken out. Probably a lot of components. Well, once you've simplified as much as you can by getting rid of components, well, it's time to actually start the study. And what I would recommend is always starting very simply. We often get tech support calls where people will call in and they've got a 30, 50 part assembly, something like that, tons of no penetration contact, tons of mesh controls, tons of connectors, etc., and it won't run. Well, the troubleshooting something like that, where you have so many kind of moving parts and moving pieces to the assembly, can be a little tough. So I would always recommend actually starting with basically the simplest thing you can, which might be very, very coarse meshing, draft quality mesh even, and even running bonded contact on all of your parts. Now, even if that's not realistic, it's going to let you make sure the analysis runs, and then you can go in and start adding your contact piece by piece in there. Also adding connectors, complicating restraints, complicating loads, etc. But when you do it, starting very simply and adding in pieces every basically step of the way, it becomes very easy to troubleshoot. When something fails, you know exactly what it is, as opposed to, well, it failed, which of these 10 loads or 10 contact sets or 10 mesh controls is the source of this. So the other thing we'll talk about is minimizing your no penetration contact. Now, obviously, that's not always possible to do. No penetration contact is necessary when you need contact stresses and just for a lot of cases. But it's also going to be the largest time sink in terms of solving. So if there's parts that may in truth be no penetration, but you're focused on basically a different part of the assembly, if these are sort of secondary components, try treating them as bonded. Try having groups of sort of bonded components with a few no penetration contacts between them, rather than running basically no penetration everywhere. The less contact sets you have that are no penetration, the faster you're going to solve. And we'll get to a little bit more on that later on. Of course, we want to make use of the simplification tools wherever we can. Symmetry, 2D analysis, and submodeling, all really good tools, and we're going to go over those in a little bit more detail today. But there's one thing you guys take away from this, it's start simple, complicate as you go. Don't try and spend sort of 5 hours setting up an analysis before you try clicking the run button. Once, you're going to cause yourself a lot of pain. So let's talk about element type selection to start with. Now, SOLIDWORKS does come with 3 different element types: solid elements, shell elements, and beam elements. And in an ideal world, we'd use solids for everything. They're nice, they're easy to use, the meshers work very quickly, the contact works very well. The issue comes with thin-walled structures. When you get into things like sheet metal or beam elements, pipes, things like that, to get enough elements through the wall thickness to accurate the stress component out of that, you're going to need lots of very, very, very small elements, and that can be an issue. So that's another thing we get calls on all the time. We get people with these massive assemblies that call in, and they're trying to do everything with solids, and we can often speed these up from things that might take an hour to solve to things that take 5 minutes to solve by appropriately using some shells and some beams where we can. And why would we do this? Well, really, we want to use the simplest element types possible that will do the job. Now, with solid elements, things with a lot of thickness, but still small enough that we're not going to get through the roof element counts, we can use solid elements for that. For example, on this sort of nozzle or flange here, the sort of manhole cover type lid and the flange, both great for solid elements. But when you get into very thin-walled components, like the actual nozzle pipe itself and the reinforcement pad around the outside, well, those lend themselves very well to shell elements. And we can also do mixed meshing with beam elements as well, and you can easily combine all three element types. Show you guys a quick example of that. Now, I'm just going to pop back into SOLIDWORKS for a second. Let's take a look at this model right here. Perfect example of something that will use solids, shells, and beams. If I take a quick look at this, we have a lot of parts in here, but some of these are actually represented with solid elements, some of them are represented with shells, and some of them are represented with beams. Now, to show you a little bit better view of that, let me actually show the mesh. So, there we go. We have solid elements down here at the brackets and also the feet on the bottom of the stand. Anything that looks like sheet metal, basically this whole separator body here, as well as the gussets between the beams, those are all done as shell elements, and then everything that looks like a beam is a beam. Now, I can go in and actually render those beams in 3D if I'd like, get a bit of a better view. But just like that, this is the type of simplification we can do. If we went in and modeled these beams and shell elements with solids, we'd end up with an element count in the millions and just basically very, very long solve times. But very possible to combine all three of those element types into one study, run them like that. The only thing you need to keep in mind when you're doing that is contact. You need to keep your contact straight between your different element types. Now, we know when we have something like bonded contact in SOLIDWORKS, let's say global bonded contact, that's going to apply to all touching faces, but that really only applies to solid elements. Where you have beams bonded to solids or shells bonded to solids or beams bonded to shells, you need to set that up manually with contact sets. And we'll get into contact sets a little bit later. You'll see the contact sets we have in here right now. There are quite a few because we've had to bond the beams to the solids, the beams to the shells, and the shells to the solids. So as long as you keep those in mind, you'll be able to use mixed meshing, no problem. So the next thing we'll discuss is symmetry and 2D simplification, and they kind of lend themselves to each other because symmetry is a step in that simplified direction, and 2D simplification is kind of like taking that all the way to the simplest possible state. So, symmetry. Well, what if you could cut your solution time in half, or by 3/4, or even more than that? Well, symmetry is going to let you do that. Very easy to use. You can find it under your fixtures, advanced fixtures, and symmetry. Right there. I'll show you guys some examples of this as we go. But very easy to go in and apply half symmetry or quarter symmetry to the model. And the only thing to keep in mind there is as long as you don't have loads in the direction of your symmetry plane. So if I just have radial loads or axial loads pushing on this, no problem. But if I have a twisting load that's trying to twist this little pulley or wheel body around its axis, we would actually need to go in and use a different type of symmetry, what's called cyclic symmetry for that. But this type of symmetry works very, very well for basically half or quarter symmetry. There are some limitations in the tool where it won't let you go to even smaller faces than that, but I'll show you just a, well, I'll say you can do the same thing. If you ever need to do symmetry on non-orthogonal faces, so let's say you had a 30-degree slice of that model, we could do it very easily. And just let me open up that pulley. Just show you guys another example of what I mean here. Let's make a new config. I'm going to call this one a 20-degree slice. And I know this is just a part, not a large assembly, guys, but the technique's the same, just quicker for me to show you on a small part. So I'm going to go in and make a quick cut on here. And I'm going to cut out a very small slice of this. We'll say something like this, maybe a 20-degree slice of the model. There we go. Now, if I were to try and apply normal symmetry to this, SOLIDWORKS is actually going to give me an error, or at least in the last couple of releases it will. If I go into Advanced Fixtures and Symmetry, try applying it there, and say there, it says the plane of symmetry is not perpendicular to the previously defined one, so it needs to be basically either 90-degree or 180-degree symmetry. Well, there's another way we can do this. If we just go to the On Flat Faces option, I can go in and apply a On Flat Faces restraint to both of these. And what I'm doing is any of my cut faces here, I'd like to go in and use a normal restraint. So just preventing translation normal to the face. Like that, that is exactly what the symmetry restraint does. It prevents normal to face translation of the nodes. Now, once that's done, I could go in and actually fixture this as necessary. I could fix the inside face. I can go in and apply a pressure load to the outside face. I'll actually do a force load in this case. And I could mesh and run this. And you guys will see it does behave symmetrically. I don't see anything crossing that symmetry boundary. This is now constrained as if it were attached to the entire pulley wheel. So that's just a quick note on symmetry. Really, really good. Guys, when you get into large assembly modeling. Now, to take symmetry one step further, we kind of showed half symmetry, quarter symmetry, going down even to a small slice of the model if you can, if you're in an axisymmetric case. Well, this brings in 2D simplification, another really, really good way to do this. So why would we want to use 2D simplification? Well, you can model things you really couldn't model before because it would just take too much time. It's available for linear, thermal, and nonlinear studies. And it's very good for plane strain, plane stress, and axisymmetric cases. So, why would we care, guys? Well, if we were to run, and this is a nonlinear example, it's a bit of a sort of worst case scenario example, but running just a 20-degree slice of this model, and this was what you guys are seeing here. It's sort of the lid of a pressure vessel with 2 O-rings on it. We were to run that just a 20-degree slice with nonlinear materials for the rubber, we'd end up with about a 3-hour solve time for that. We cut this down to a 2D slice of the model and run it again, we can actually solve it in less than 20 seconds. So that, of course, you're not going to see that sort of reduction every time, but even if we went in and refined the heck out of the mesh in the contact region there, got a very, very refined mesh, we'd still solve in less than 1 minute. So where possible, 2D simplification is going to save you a lot of time. And here's a quick example of this, guys. Now, why might I want to do this? Well, if I had something like this expansion joint here, I might see some steam load on the inside and maybe some thermal expansion loading as well. Well, I could look at something like a 3D or quarter symmetry or half symmetry configuration, but I might even go in and look at something like just a very small slice. So just cutting the model in half and then taking a small slice of that half, something like this. If I wanted to accurately capture my bending through the bellows, well, I'll show you what my mesh might look like. Just for a 20-degree slice of that, I have probably close to 1 million elements in here. Yeah, about 970,000 elements for just that one little part. Well, this is a perfect example of when to go two-dimensional. Instead of going to something like this, we have an axisymmetric case that's also symmetric end-to-end. So I can actually run down and do a thermal stress study just like this and find out exactly what's going to happen to that model. So still go in, apply our loading, the pressure loading, thermal expansion loading, restraints, etc. If I'd like to, I can even take a look at this in 3D. By right-clicking and saying Show as a 3D plot, I'll take my 2D model and bring it right into full 3 dimensions. Just like this. And this is doing exactly what you think it is, guys. It's basically just faking it. It's revolving the color plot of the 2D plot around the axis, but really helps with visualizing what that looks like. Great for including in reports and showing to other people as well. Now, a couple more things that we will talk about. We'll get into some submodeling in a moment as well, because that's another really good simplification tool. But I'd like to talk about automatic contact set definition first. Everything we've talked about so far has been sort of simplifying or reducing the amount of solve time on the model. But we're also going to take a brief aside here and talk about simplifying some of the setup and speeding up the setup of the model. When we have 30 or 40 parts in an assembly, or sometimes less, sometimes more, we even have more touching faces than that. So we might very easily get into dozens or even more contact sets. Well, creating those can be a very, very tedious process. You're going through, selecting faces, adding them. Well, we have the option to automatically find contact sets. And I find a lot of people we talk to aren't really aware of this. It's not a new feature in SOLIDWORKS, but it is a very, very useful feature. I'd like to show you guys how to use it. Okay, bear with me for 1 second, guys. There we go. That's the model I'd like to use. Now, going into something like this. This is a model that does have quite a few parts in it. It's not a large assembly, but if I were looking at an exploded view of this, I do have multiple parts. Even with this, like 2, 4, 6, 8, they call it 10 or 12 components in here. The contact setup could be pretty tedious to do. If I look at a study that's been done and take a look at the contact sets in here, you'll actually notice I have a lot of no penetration and bonded sets. We've got 13 contact sets in this fairly small model. So imagine if we got into something twice this big or 10 times this big, we could have a lot. Now, how do we use this auto contact sets tool? Well, let's talk about it. We'll go in, and I'm just going to start a new study here. Now, to run through contact sets, we just right-click the Connections folder, go to Contact Set, and here it is, guys, right at the top, the Automatically Find Contact Sets tool. So, if I go down to Automatically Find them, I have an option. I can either find them for any touching faces, great if all your geometry is size on size, or I can go non-touching faces. If you have small manufacturing clearances in there, if you've got 1 thou or 10 thou gaps in there, you can go in and set a tolerance range. SOLIDWORKS will find any face pairs within that tolerance range and give you the option to do a contact set. But for this example, everything is size on size. So I'm just going to say find touching faces, and I won't do specific components. I'm going to go up and select the whole assembly from the top of my tree and say find contact sets. Well, here we go. I have all the contact sets in the model showing up in this list, and I can go in and add them. I'll show you what we'll do. First one, well, that's actually first 2 in fact, in here, are this center tube being bonded to these outer plates, and those should be bonded. So I'm actually going to select both of those, change my contact type to bonded, and add. Well, let's look at the third set. Well, that's actually going to be bonded as well. Fourth one, that's no penetration between this sort of bushing here and the sidewall. So I'll set that one to no penetration. 5 is that one on that side. That's going to be a bonded set. 6 is no penetration again. 7 is bonded. 8 is bonded. Then the last 2 are both no penetration. So I can highlight them both, no penetration, and add. So very quickly, guys, we've just found and added 10 contact sets in there. Now, that was a pretty quick example, but you can see you can very quickly add, let's say, 30 or 50 contact sets in a matter of minutes, as fast as you can click and select what they all are. So that can be a very good time saver in large assembly analysis. Now, as I mentioned, great for large assemblies, also works for those non-touching faces, so if you do have clearances in there, don't worry, we can still help. Now, this is a great time to talk about submodeling, and this kind of plays into the symmetry and 2D simplification we talked about earlier. So what is submodeling? Well, submodeling is a way to zoom in on one component while still having it behave like it were attached to the rest of the assembly. Now, this is a great way to simplify complex analyses. Now, you may wonder, sort of, how do we make it behave like it were attached to the rest of the assembly without running the whole assembly? Well, we do run the whole assembly, but we can do it with a very, very coarse mesh. And this is kind of the layout, guys. So we would start with the whole assembly model, but just a very, very coarse mesh for it. Now, this will not give us accurate stresses at all, but even a coarse mesh will give us accurate displacement results in the model. So it will accurately calculate the stiffness and accurately give us a deformed shape out of the model. So once we run that and we get the overall deformation, then we can create a submodeling study. What we do, we go in and select the components that we'd like. Once we select it, and in this case it might just be that little cross beam on the frame, well, it then creates a study with just that one beam, but it transfers the displacements from the master model onto the edges of the submodel. So the ends of the cross beam here, those 2 edges that would be welded onto the frame rails, those are forced to twist and behave like it were connected to the master model. So what we can do now in that one component, we could try finer and finer meshes to run a convergence study on the part. We could even try small design changes, like going in, making weight-reducing cutouts, changing geometry slightly. The only thing to keep in mind there is, for example, you look at this picture on the very bottom right, we've got a weight-reducing cutout down there. Well, if that's going to be enough of a stiffness change that it would affect the overall displacement, you'll want to go back and rerun the parent study, again, with that little weight-reducing feature in there. That's going to recalculate the displacement, and then when you go back to the submodel, it will retransfer that new, slightly less stiff boundary condition onto the edges of your submodel. So, very quick, very easy to do. I'll show you another example of this, guys. That would be something like this. So we have a scaffolding here, and this is something where it's sort of verging on a large model. We have a lot of pieces in here. The main thing that's going to take a while to solve is the no penetration contact between these hangers and the pipes that they kind of sit on down here. So let's actually take a look at this. I'm going to activate this configuration. And we'll take a quick look at the mesh. Now, you'll see what's been done here. We've used beams where possible in some of these. We've used shells where possible on some of these as well. But in the contact areas where we want accurate contact, let's say there maybe up here, we've used solid elements. But right in here, you'll notice the solid elements on this hanger are not nearly refined enough to give me an accurate stress condition there. But this will still give me the overall deformation of the structure when I have some loading on it. And in this case, I've got a loading on the top of the structure. I also have some side loading on here as well, pushing part of it sideways, and I also have gravity acting on it. So when I go to run this, I'll end up with something like this. So we can see this deforming, you can see the cross bracing deforming in here, but if I wanted an accurate idea of what the stress is right on this little hanger, well, that's a perfect case for a submodel. So what do? Well, you just right-click on your top-level study, you say create a submodeling study, and then it's going to ask you which components to select. You'll choose your components, and it will create a study like this. I'm just going to activate the configuration. So with the submodel, we can actually zero in on just one of these connections up here. I'd like to look at one of these hangers and find out what is the true stress in that contact region. Now you'll notice it does take a second when we switch over to the submodel here. It's sort of sitting here and thinking. It's just going through and suppressing all of the bodies and transferring those boundary conditions again. But this is what we may look at in the submodeling study. Just a few components, but we can see very detailed results on these. Again, the boundary conditions at all the edges here, at all the cut faces, these faces are deforming and behaving like they're connected to the master model. So I can now run through, try a much more detailed mesh on something like this. We can run through and do a mesh like this, very heavy mesh along our contact zones. We see how deep those stresses go. And I can start looking at detailed stress results on the part. Now, they still do deform and behave just like the rest of the study. If I go through and animate this, you'll actually see how these flex. And we don't have actually any loading on here. You'll notice the load on this study has been transferred automatically from the other model, from the master model. But so behave very seamlessly, guys. It's a great tool to try out, and I'd highly recommend you try submodeling. It's a tool that can take very large assembly work and simplify it down into runs that take minutes instead of hours to do. Now, we have talked about a lot of things here, guys, and we've got about 5 minutes left in this, and I'm going to talk about solver options for large assemblies. Now, how many solvers are you guys familiar with in SOLIDWORKS? Now, probably two of them. You're probably familiar with the direct sparse solver and the FFE plus solver. Those are the two defaults. Now, the direct sparse is actually a direct numerical, or sorry, a direct solver. So it's actually going to solve the displacement field of the assembly directly. So using basically matrix techniques, matrix inversion, matrix simplification, all of that fun stuff, it directly solves for X. Now, FFE plus, which is the fast finite element solver, that's a little bit different. It does not actually go through and compute the solution to X. It iterates. It actually assumes a solution for X. It runs that, balances the equations, looks at the error, and keeps basically iterating that until the error is within an acceptable limit. So, an iterative numerical solution versus a direct solution. Now, what are they good for? Well, and before we do this, we are going to talk about a little bit more, guys. The last few years, they've added 2 new solvers in here, and we'll talk about both of those. But first, you need to understand what the existing solvers are good for. Now, direct sparse is an excellent solver for contact. When you're dealing with small models, there's really no difference in solvers, but sparse will do a much better job on solving no penetration contact, especially when you have lots of contact sets. But it's really only good for small models, things with sort of less than 500,000 degrees of freedom. This solver uses a lot of RAM, and it will slow down dramatically as your model size increases. And it's very possible here to have your analysis run out of RAM with the direct sparse solver. And when that happens, we go from what we call an in-core solution to an out-of-core solution. When you don't have enough memory to basically hold the entire solution in your RAM or your memory, SOLIDWORKS will start basically writing to its page file, or basically the hard drive, and starting to store data on the hard drive. Now, instead of quick RAM calculations, you're actually reading and writing tons of info from your hard disk. That's what we call an out-of-core solution, extremely, extremely slow. And that's kind of where the direct sparse fails with large models. Now, the FFE Plus, it's very fast for large problems. It's actually typically the fastest solver, uses much less RAM, less than 10% of the RAM of the direct sparse solver, but it can have problems when you get into no penetration contact, a lot of no penetration contact, or materials that have really, really different stiffnesses, like very stiff and very soft materials. Now, they both kind of have their advantages and disadvantages. We used to sort of have to switch to FFE Plus for larger models because it was the only way. Well, we have two more solvers that may help, guys. We have something called the large problem direct sparse and the Intel direct sparse. And I believe the large problem one was introduced back in, I want to say 2013 or 14, and then the Intel direct sparse was just introduced a year or two ago. So the large problem direct sparse, what this is for, it's for models that are too big for the direct sparse solver, ones that will go out of core. Now, what it does, it actually uses some memory algorithms to not send the entire solution into memory, just the parts it needs. So the nice thing there, even if it would go out of core for the direct sparse solver, because the large problem direct sparse is sending less info to RAM, you can have bigger problems and still have them remain an in-core solution, a fast solution. So that would be my first recommendation. If you're getting basically any out-of-core warnings with the direct sparse solver, try the large problem direct sparse. You'll probably have some good luck with it. Well, recently we have a new solver. This is the newest of the four, the Intel direct sparse solver. And this is actually a direct sparse solving algorithm developed by Intel. This was introduced as a faster solution to the old direct sparse solver. Now, I would highly recommend trying it. It uses enhanced memory allocation, and it uses multi-cores better as well, and this can be much, much faster than the standard direct sparse solver. It can still go out of core. If that happens, you may need to switch to the large problem direct sparse solver, but for most cases, this can be anywhere from sort of 10% to 40 or 50% faster than the old direct sparse solver. So try that out, guys, and it should help. Thank you very much for attending. I hope you get some good tips and tricks out of this that you can use on your own large assemblies.